Hello, everyone, and welcome to another SETI Live. I am your host, Beth Johnson, Communications Specialist here at the SETI Institute. Thank you for joining us, everyone, and welcome. And welcome to our viewers from around the world. Please let us know where you are watching from today. Joining me today is Peter Jenniskens, a senior research scientist here at the SETI Institute and a co-author on a new paper published in Icarus detailing the discovery of Buckminsterfullerenes, or Buckyballs, inside an unusual meteorite called Alamahata Sitta. Thank you for being here today, Peter.
Pleasure.
So let's start with the main part of the story. Will you please explain what a Buckminsterfullerene is for our audience?
I think the main part of the story is really the meteorite, and it's a very peculiar properties. Buckminsterfullerene detection came as a real surprise. Before I start, let me first show you my brand new office, as we just moved to new building at SETI. This is the place I live now.
Wow, that's fantastic.
With a stellar view.
That's really nice.
It's nice to be back in the office, but it's still very scary because all the COVID concerns. We're having the FDL program and RIO programs now in person this year, and so it's all very, very exciting. So yeah, that makes you dream again of going to faraway places. And in 2008 I traveled to Sudan. I went to the Nubian desert with a colleague, Professor Mawiya Shaddad, an astronomer at the University of Khartoum. And he turned out to be a great organizer. So he managed to get a busload of students to come with us and check out an area where a small asteroid had crashed. And that asteroid was seen coming in. So it was tracked for 20 hours. It then broke apart in the atmosphere and broke into pieces, and all those pieces scattered and were somewhere there in the desert. So we didn't know if we would be able to find something. As a matter of fact, the explosion had happened so high up in the atmosphere. Nobody had ever found a meteorite from an explosion that high up, because it means the meteorite was very fragile, and so presumably very little survived. But it turned out that this was a fairly big asteroid as far as meteor fireballs goes. This thing was by 2 by 4 meters or so, so it was sort of the size of a small car. And that was big enough for some material to later be found. And so we created our own road going deep into the desert, and lined up all the students and did a grid search. You put everybody on a line and you go and see if you can find something and see something. And it took only 2 hours for one of the students, Mohammed Al-Amin, to find that first little fragment. And that, of course, was really exciting, because this was the first time we had a piece of material in hand from an asteroid that was spotted in space. And so you could compare the properties from space with the properties of meteorites that we can study in the lab. But then something very strange happened, and we were still sort of celebrating and about having found one piece. When we found our second piece, it turned out to be very differently looking, very differently looking. So the first piece was sort of like more of a grayish stone. There was some layering in it, which I had never seen before. The second piece was like a coal briquette. It's like a black, scruffy looking, really dark rock. And we found a couple of those in that second day of search. And so at that time, we knew this was so weird and this was so fresh looking. This had to absolutely come from our asteroid. But what was it? And at the time, I had no clue, And the third day of searching proved even to be more remarkable, because suddenly we were finding rocks that looked like ordinary gondorites, like meteorites you normally find, and rocks that looked like concrete. And there was just such a variety of stuff in the finds that every single find was like Christmas present. You open it up and there's something unexpected to be found. And so so this proved to be not just a really unique case of an asteroid spotted in space and then tracked on land the first time, but it also proved to be a really interesting meteorite. And this was the first time that a meteorite fall was sampled on such a scale that we had many pieces of it, and we could really tell, that there was all this variety, this difference in the rock. Mm-hmm. So that set up a whole bunch of additional studies, not just to understand, what this rock was, but also how could it have so many components. And it turned out that the black, scruffy-looking rocks we found were called urealites. It's a very rare type of meteorite. This was the first time that a urealite was recovered. That was also a mixture of things. This was called a polymicted urealite. It was like a breccia. It had different types of rocks in the same object. And this was the first time that such material was found. And so that was very exciting. It was a urealite. Those other types turned out to be ordinary chondrites, ancetite chondrites. Ancetite chondrites are very rare to found, and this thing had many different types in it. Even there were some carbonaceous chondrites, which we call primitive, sort of unaltered type of a meteorite. And there were things that look like blobs of iron, and it's just incredible. So in recent years, we've continued to look at these rocks, to study them, and recently in a program led by Serena Goodrich, who's a urealite expert, we've been examining really the full diversity of meteorites that are in the University of Khartoum collection. So try and understand what different meteorites were part of this asteroid. And it's a slow process. Yeah.
How many fragments did you guys end up recovering all told?
600 plus. So it's a huge number. Thanks to the fact that the university was able to bring huge numbers of people out. At one time, they had 105 people searching.
How big was the object that entered the atmosphere? Do we have
the size when it came in was like a small car. So it was big as far as not big for asteroids, but big for asteroid impacts as we know them. It was a fairly big rock, but from all of that material, only we think about 39 kilos survived to the ground, and of that 39 kilos, we recovered about 11.
So, wow! Yeah, that's still a lot.
Yeah. So exactly. So 600 pieces, and most not than the biggest is like your fist. Most of them are really small, tiny pieces. We really wanted to recover pieces of different size to sort of understand what the different objects were at different sizes.
And so what was the first thing you guys started kind of looking at to analyze these meteorites?
So one of the earliest discoveries was that urealites. Let me tell you a little bit about urealites. What those are. They are just the weirdest among meteorites. Meteorites typically fall in two groups, just like asteroids. You have the groups that are the stony ones that sort of are associated with the inner part of the solar system, including where Mars and Venus, Earth and Venus and Mercury formed. And then there are the carbonaceous chondrite, the primitive meteorites that formed further out, probably beyond where the big planets were initially formed. And that difference is really strong. So you can see, if you look at specific elements in the rock, you can see that the compositions are different. So there are certain isotopes of chromium, for example, that are that are clearly different between oxygen isotopes, are clearly different between the two regions. And if you look in an asteroid belt, you can also see that sort of difference. You see a whole bunch of things that look like what we call S-class asteroids, which are stony class. And then you see a whole bunch that are C-class, which, you know, the stony ones have big, strong absorption bands for minerals. The C-class is more flat looking. So the stony ones have these a sort of color to it, and the carbonaceous one just look dark and gray. And that distinction is quite clear in the asteroid belt. And the outer asteroid belt is mostly the carbonaceous ones, the C-class ones, I should say, and the inner asteroid belt has a lot of the S ones. Now the Eurolites fall among the S ones. So they were formed somewhere in the area where Mars and you know, maybe the Earth formed, and then somehow evolved into the asteroid belt. So they come from our area, but they contain carbon. So when the Eurolite parent body was formed, there was a significant amount of carbon still in it, and you know, the Earth, when the Earth was formed out of material that is more similar to ancestite chondrites, and it no carbon, no organics. Right. And so this object is sort of a strange duck in the zoo of asteroids we have out there, and it was probably formed very early on. We think that it experienced heating from radioactive decay of radioactive isotopes we had in those days. It got hot to the point where almost the whole thing melted. But in reality, only the minerals melted that were fairly low melting point. So all the normal minerals, the abundant ones, the olivines, the pyroxenes, that type, they stayed solid. So if you take a piece of a Eurolite and you look for oxygen isotopes, you'll find that each little piece has a different oxygen isotopes. So there was no melting, no mixing going on. Each piece still shows that sort of diversity that there was originally. But if you look at the composition of the rock, you see that certain minerals, certain elements have gone down a lot in their abundance. So this thing got hot. There was some sort of volcanism, some sort of flowing of you know, fluid minerals that got lost, and then when the object was right at that stage, before the whole thing melted and an iron core and a crust formed like on the Earth, just before that moment, it got smacked really badly, and the rock went into pieces. All those pieces by gravity came together again and created one, or you know, a bunch of different objects. And that evolution is sort of unique to, you know, anything else we know of in our meteorite collections and in asteroid belt. And so this object has sort of an interesting window in the universe. And apparently, after the object had sort of smashed into pieces and reaccumulated, it was again hit by a lot of other things. And a lot of other things were ancestite chondrites, ordinary chondrites, even some carbonaceous chondrites, everything else that we're finding mixed in with these Eurolites. And so that's another sort of interesting window on the early solar system, because this object was collecting stuff from its environment. So you're sort of sampling its environment, and its environment had a lot of ancestite chondrites in it. So, you know, so we're thinking sort of Mars position, so sort of in that range where it you know, lived in those days.
All right. Well, I want to hear more about it, and I know we're going to get into what you found with all of this carbon. But let me take a second to welcome people who are watching. It looks like we're watching from Spain, Sweden, Chicago, Nigeria. Let's see, England, Canada, Louisiana, New York State, Northern California, not far from Hat Creek. Welcome. So that's great. There's a lot of people watching from a lot of different places. That's fantastic. So the key to this particular story today is all of that carbon, right?
The key is the urolite and the fact that there was organics found. So when we early looked at these various pieces that were part of this rock, and this was found by a group in France, headed by Christine Blin and by Hassan Sabah, the people who have the equipment and a really nice instrument to look for organic compounds in meteorites. I brought some samples to their lab with the idea that they could test what type of polyaromatic hydrocarbons there were in a sample. Polyaromatic hydrocarbons is a specific organic material that is, rather sturdy. You find it everywhere. It's also a diagnostic. It also has quite a variety of compounds to it. And so by studying these polyaromatic hydrocarbons, we could learn about the processes that this urolite parent body and then its daughter products later went through. And so what Hassan found was that there were polyaromatic hydrocarbons not just in the urolites, and urolites you expected, because urolites has a lot of organics in it, a lot of graphite, but there were also polyaromatic hydrocarbons in the non-urolites, in the andesite gondorites and in the ornate gondorites, all those other rocks that were there. And that was a surprise. That was just not expected, because those rocks normally don't contain that type of organics. And so we soon realized the signatures were similar. The paths looked similar, but there was a variety depending on the different rocks we were looking at. But we soon realized that that had to be because the paths originated in the urolites, and with all these impacts and collisions that happened, somehow that material evaporated, and it got into everything. It just contaminated everything, including, the andesite gondorites, especially the porous ones. Everything, ordinary gondorites that were porous and so on, they had all these organic compounds in them. So all this volatile stuff in the rock got mobilized. It's just made everything dirty, basically, made everything a mess. And that is an interesting observation. It basically shows that what the effect was of the attacks on the whole environment.
So what comes next in the research after discovering all of these polyaromatic hydrocarbons?
So that's where things stood until a few years ago, when we started looking at more samples, at more urolites, and we realized that it would be good to know what the different part content was of different urolites. If we could find differences in the individual rocks, we could perhaps relate that to where we found meteorites in the strewn field. We were just interested in learning everything about this little asteroid 2008 TC3 that came crashing down. And so I brought more samples to the team of Christine and asked them to have a look at it and see if they could give us more signatures. And so they started looking at a few of the urolites in detail. And then, to our big surprise, they did not just find paths, but they found buckyballs. And buckyballs are so this picture shows on the left-hand side a piece of the urolite that's really sort of black-looking stuff, and on the other side is a piece of a non-urolite, so it's more crystalline, more olivine, pyroxene type material. And so in the urolite material, not in the other ones, in the urolite material we found these buckyballs. And I don't know if you know what Buckminsterfullerene is, what sort of molecule that is.
I know it is basically 60 carbon atoms, sort of all put together in kind of a sphere.
You like playing soccer? It's a soccer ball.
Like that, right?
It's basically a soccer ball. So if you look at how a soccer ball is made, it's basically made out of hexagons and out of pentagons. In this case, it's pure carbon. These are all carbon atoms that create a cage like a soccer ball. And the Buckminsterfullerene is specifically the one that has 60 carbons in them. And so it's called C60. But there is a whole variety. If you show the next picture, you can see a mass diagram, mass spectrograph. This is the detection of all the compounds that were found. And you see there C60, that's the most abundant, that's the strongest signal. But you can also see there are a whole variety of other compounds in steps of adding 2 carbons to this ring. So these are not perfect spheres. They are sort of becoming more elliptic when you go to bigger sizes. But it's the same type of molecule. It's basically a cage of carbon atoms. And these cages are very interesting because they have been found in the interstellar medium. So it looks like certain stars create these compounds in their outflows, and they are found in the diffuse interstellar medium. So they are part of the stuff our solar system was born from. It's the stuff out there. Except if you look at primitive meteorites, carbonaceous chondrites, you don't find them. they've gone. There's also certain types of large aromatic hydrocarbons paths you don't find, and so there are processes that these molecules can't handle, and they will ultimately be lost and be at very low abundance. And that's the thinking. But in Alamahata Sitta, in this strange Eurolite, in the Eurolites themselves, there are buckyballs.
So what does this mean for these meteorites? What comes next?
So that was a really interesting debate we had in our group. It really depended a little bit on your background and sort of which scenario you favored, but every possible scenario has some difficulties with it. And we first made sure that it wasn't an instrumental problem. So in the past, people had found buckyballs when they used a strong laser and evaporated stuff from the surface. If your temperature goes up too high, then you can make buckyballs in the plume. You create, it's chemistry you create. And we concluded that in the setup at the University of Toulouse, perhaps we were making also some of the small carbon chains that we were seeing in the beam. But we did not make the fullerenes in the beam. We did not see the fullerenes, for example, in Murchison, which is a primitive carbonaceous chondrite. We didn't see it in Alamahata Sitta, and so that sort of in Allende, which is another carbonaceous chondrite. So right. you find it in the Eurolites. You don't find it in the primitive meteorites with this instrument. So we really looked to make sure that it was not instrumental. Okay, so now it's not instrumental. Where does it come from? It's possible, and I'm sort of inclined to think that it's somehow formed with all these impacts. So you have this graphite in the rock, and you have also what's called nanodiamonds. So the graphite, by really big impacts, got changed into tiny little diamonds at places. And there have been laboratory experiments that turn those little tiny diamonds into sort of onion ring structures, but those onions don't quite look like what we are seeing in this meteorite. And so, and if you really want to make buckyballs, you need very high temperatures, like 3,500 K or so. So such high temperatures you typically don't have with the impacts that happen on the Eurolite parent body. And so I'm sort of inclined to think it was made from these impacts in these strange objects because we don't see it in carbonaceous chondrites. On the other hand, it could also be that it is in this strange meteorite because the meteorite is strange. It was formed very early on in the solar system. at a time, when there was radioactive aluminum and other things that were put into the solar system by, massive stars that were in our environment. So it could have been that material that this stuff was came in with stellar grains of sorts, and was preserved in this urolite since its formation, basically. But then, of course, that implies that somehow these molecules survived the chemistry and the heat and pressure and so on in that urolite parent body for a long period of time. So that's another difficult scenario to really, be happy with. So we were stuck with these various scenarios as to explaining our results, and that's where we left it. We basically published the paper saying, look, we found this, we think it's real, but where does it come from? That's really the clue.
Wow. So this is kind of exciting. I'm really excited to hear about this. I'm going to say hello to a few more people before we take audience questions. So feel free to post questions if you have them for Peter, and I will pass them on. It looks like we have Woodlands, Texas, France. There were a few more. India, here in San Jose, which is where I'm at. That's really cool. And I think that's kind of it. So thank you everybody for watching. And in case I forget, thank you, Moon, for the super chat. Very appreciated. Okay, so some audience questions. Lily is asking, is this meteor, is this a big a find as, say, the Murchison or the Allende meteors?
Sorry, repeat that again.
Is this meteorite find, would you consider it as important as finding, say, Murchison or Allende?
In my eyes, yes, but that depends on what field you're in. But I think to have a meteorite like this studied opens up windows into the universe, just like the find of Murchison and Allende did. Allende and Murchison were very important because they fell at a time when the Apollo program ramped up, and they were basically the samples that the researchers were studying to prepare for being able to investigate the lunar samples. And so that's what made Allende and Murchison really important meteorites.
This is kind of an intriguing question. It's not quite what we're talking about, but I'm interested. What's the possibility, this is from Moon on YouTube, what's the possibility of a meteorite originating here on Earth and basically coming back later to be found?
So it very much depends on this later. And it depends on so it's difficult to eject meteorites from the Earth because the Earth has so much gravity that it's not easy to speed things up to the escape speeds of over 11 kilometers per second that you need for something to get completely off the Earth. It's a lot easier to do with Mars, and for Mars we know it works. So we have meteorites in our collections that come from Mars. There's big impacts, some material makes it into space, and then after a certain amount of time, it gradually gets closer and closer to the sun, and there's the Earth, and then it can hit us. But in the case of stuff coming from the Earth, if you go back as far back as the Ordovician, you're talking about a very long period of time. And so small rocks are probably cleared out completely from the Earth environment. So it's unlikely that a rock from the Ordovician still floats around in space to now hit us. But it's possible that a rock from the Ordovician somehow fell on the moon and it sits there for us to collect. So that's an interesting possibility. If it's possible to get stuff from the Earth, then the moon is maybe a fantastic garbage bag for collecting this stuff. And giving us a sort of a nice view of our history independent of what we can do on Earth.
So there we go. We need to send our rock hunters off to the moon to go find
Another good
meteorites.
reason to go back to the moon.
Okay, it looks like the only other question I think we had was actually answered, which was about finding the buckyballs themselves. So I think we're about ready to wrap up then. Peter, did you have any last thoughts you wanted to share on this find?
No, keep looking around. You know, there may be a meteorite in your backyard. We're running a camera network in California and Nevada, but there are networks all over the world now where people try to recover a meteorite that has a known impact trajectory. So we know what angle it came in and from what part of the asteroid belt. And we like to find out where our meteorites are coming from. We try to play this game with 2008 TC3. We have a very nice orbit on it. We have samples in hand, but it turns out there is not one debris field in the inner asteroid belt. It's coming from the inner asteroid belt. That's what we know from that. But we don't quite know from where in the inner asteroid belt it comes. It's a puzzle, as one of many.
Mm-hmm.
But yeah, if you find a meteorite and we have a trajectory on it, then it would add to the collection we have so far.
That would be fantastic to get. And just as a reminder of personal interest to me, if you spot a fireball, you can report it to the American Meteor Society. Yes. And that always helps us find some of those trajectories that we might not have caught on camera, or we might have caught on a couple cameras and we need a third. So your eyesight does help us. Thank you, Peter. Coming up next week on June 29th, we have a special Ask SETI Anything SETI Talks event at noon Pacific, 3 p.m. Eastern. Please register at the link that has been shared across all of our streams. You can also, you'll receive a link to ask questions in advance of the event. So if you have any questions on any of our science, from SETI to meteors to exoplanets, we will have several different scientists there to answer those questions, and we would love to have all of you watch.
And I believe that the paper of this interview is also linked through the chat, yes, so people can access it. Many thanks to Christine and Hassan and Maria and all the others part of our team to come up with this great result.
And thank you everybody for watching. And just as one last reminder, we are a 501c3 nonprofit. So all of your bits, your subs, your super chats, and your stars go to supporting this wonderful outreach program. So thank you very, very much everybody for watching.